Hello everyone, welcome to the course on biostatistics and design of experiments. Today I am going to talk about non-parametric tests. Okay. So far we looked at parametric tests, but today it is going to be non-parametric. What is this non-parametric test? So it assumes in a parameter standard sampling distribution like your T distribution, F distribution, Z distribution, normal distribution, all these are called standard parametric tests, and you have corresponding tables, and then we used those tables to find out the p values given the degrees of freedom and so on. But then you can always have data, okay, which does not follow this type of distribution. Actually they are distribution free data. Okay. We will look at them, what are these distribution free data. Then we still need to use some sort of a test for comparing distribution free data, right. So they are called non-parametric tests. So there are three cases which requires the use of non-parametric tests. Okay. What are those three cases? Okay. There exists severely unequal variance between the groups, that means they do not follow the homogeneity of variance. What is that homogeneity of variance? That means we assume that the variance is almost similar from each group. Okay. The distribution of the data for the response is not normal, that means they do not follow a normal distribution. Normal is mean, median, mode are all is same, but here they are very different. Okay. Or they have not, it is basically ordinal. Okay. The data could be ordinal, that means it is not interval scale, there are no interval scale type of measurements. Okay. Like we have pH as a function of time, temperature as a function of time. Okay. So you have the time as your interval. Okay. In such situations, okay, then obviously we need to use something else, and they are called non-parametric type of data, and so we need to use non-parametric test. Okay. So homogeneity of variance is violated, and the data is not normal or the data is ordinal, that means there is no x axis like a time, for example, pH versus time or temperature versus time, it is more of an ordinal time. Okay. Then we use the non-parametric type of test. You have similar to each of the parametric test a corresponding non-parametric test, and we will spend some time on each one of them as well. So suppose I am comparing two independent samples, generally we talked quite a lot, right, two sample t test. Okay. Then for a non-parametric we use something called Mann-Whitney or Wilcoxon rank sum test, Wilcoxon rank sum test. If you are comparing dependent samples, that means the pair t test, you are using the same subjects for giving the placebo as well as the drug, you are using the same subjects for giving the drug A and drug B. Then we use corresponding non-parametric test is sign test or Wilcoxon signed rank test. Okay. If you are comparing k independent samples, that means you are comparing many drugs, I want to see whether there is a statistical difference between drugs. We used to do ANOVA, one way ANOVA, right, you remember all this very well. Corresponding non-parametric test is Kruskal-Wallis test. So these are the tests you need to know, especially for non-parametric data. Like I said, when do you know it is non-parametric? If the homogeneity of variance is violated, or it is not like a normal distribution, okay, or some sort of a distribution like T or F or Z type of distribution, and then the data is ordinal, there is no variation with respect to time or something like that, then we need to use these type of tests to determine for comparing independent samples, comparing dependent samples, looking at large number of samples and so on. Actually later on we will also talk about what is this homogeneity of variance, how do you find out later on, but as of now we will talk about these various non-parameter based tests. Okay. So let us look at this Mann-Whitney Wilcoxon rank sum test. When do you use it? When the populations are not normally distributed, the sample size could be small, so it is very difficult to assemble them as a normal. Response is ordinal, that means integer numbers type response. Okay. So what do? We can say H naught, that is the null hypothesis, is you are looking at distribution of population A and population B. The null hypothesis could be A is equal to B. The HA, the alternate hypothesis could be one of them, right. A is not equal to B, that means population A and population B are not the same, or population A larger than population B, that is A greater than B, or population A is less than population B, that is A less than B. So, these could be the various types of alternate hypothesis, and this could be the null hypothesis, just like the previous parametric based test actually. Okay, let us look at some problems later on, but initially we are looking at A is equal to B, distribution of A and B are same, whereas A is not equal to B, right. Here A is greater than B, because A is shifted to the right. So, for example, we can say, is there an evidence that the values of A are generally larger than that of B? If this is on this side, we can say, is there evidence that the values of A is generally less than that of population B? These are some good references which I am talking about here, it is worth looking at these references books, which gives you quite a lot of examples related to health sciences and biological sciences. So, what do we do in this? We rank all the data. So, suppose we have any observation for sample A, NB observations for sample B. So, we combine all the results together and rank them, that means 1, 2, 3, 4, the smallest value called 1 and so on, and then put them in ascending order, that means smallest value at the bottom, that is 1, then the next larger is 2, like that, but you have to combine both sets. Then sum the ranks of the observations from population A separately, that will be called WA, sum the ranks of population B, that will be called WB, assign average rank to these tied observations. Suppose if I have a data 16 in population A and I have another data 16 in population B, what do? I will add 2 ranks, divide by 2, that is called the average rank. So, the alternate hypothesis is A less than B, reject H0 if WA is smaller than WB. So, it is exactly like that. So, if WA rank is smaller than WB, then A less than B, that is the alternate hypothesis, and if WA is big than WB, then alternate will be A greater than B, and of course the null hypothesis will be A equal to B. So, you understand. So, what we do is we combine all the data and then rank them, the smallest will get rank 1, then next one will be rank 2, like that, the largest will get the highest rank, and then you sum all the ranks related to A and call it WA, sum all the ranks related to B, call it WB, and then if WA is smaller than WB, the alternate will be A less than B. If WA is bigger than WB, then the alternate will be A greater than B. So, you understand this, and then there is a table for this, there is a table also for ranks, and then we can reject the null hypothesis or accept the null hypothesis based on the statistics and the table comparison, just like the normal parametric test. Let us look at a problem, and before going to that, this is the table, this is the table, as you can see, N is the sample size of the group with the smaller rank, N is the sample size of the group with the smaller rank, and this here you have the 2 alphas, the 0.05 probability and 0.01 probability, so N, this is the smaller rank, sum must be less than in order to reject the H0, for a one-tailed test. Similarly, you also have a table for the two-tailed test. So, this table contains values, the smaller rank sum must be less than in order to reject the H0 for a one-tailed test. Do you understand? So, we have here sample size of the group with the smaller rank sum, and this is the sample size of the group with the larger rank sum. Do you understand? Now let us do a problem here. This problem is taken from this particular references, it is Journal of Laboratory Clinical Medicine. We are looking at the fasting glucose levels of patients who are having Huntington's disease and those of the control. So, glucose is given orally to those with Huntington disease as well as to a group of the control, and then after 5 hours the data is collected, that is the glucose present in terms of mg. The hypothesis is the glucose greater for patients with Huntington disease, that means H0 is control equal to Huntington, we will call it C is equal to H, HA is control is less than Huntington. Do you understand? Control is less than Huntington. So, C is less than H. So, as I said this example is nicely taken from this reference. Okay, so, what do you do? This is the data. So, you have the control the glucose 10 control and then 11 with Huntington, okay, 11 with Huntington, 10 with, this is the glucose levels after 5 hour after oral ingestion, okay. This is the value, this is the value. So, obviously, we cannot consider this as a normal distribution because it is sort of ordinal. So, what do? We combine all these data. So, 11 plus 10, 21 sets of data, and then we arrange them in the ascending order, that means increasing order. So, we give 65 starting, then go right up to 100, this 100 will come there. So, that will get a rank of 21, 65 will, there are two 65s as you can see here. So, this will get a rank of 1.5 because 1 plus 2. So, these two 65s will get 1.4, 1.2 rank. Do you understand? Then comes 73, then comes 75, then comes 77. There are two 77s here, 177 here. So, this will get rank of 5 and 6. So, 5 plus 6 by 2, 5.5, 5.5, like that you rank all the data. Okay. Now, some of them belongs to A, some of them belongs to B, do not forget that. So, we need to separate the A's together and the B's together and then add up to get WA and WB. Okay. Okay. So, again here we are putting down these ranks here. Okay. So, as you can see here in this particular case these two got 1.5 rank and then you have the 3 rank and so on, okay, right up to 21, this got the rank 21. So, now if you add up all these ranks that get you W control, if you add up all these ranks we get the WH. Now, the goal is to tell the null hypothesis is the control is equal to H, okay, or control is less than H, that is the alternate hypothesis. So, we need to go to the table to cross check. Okay, let us look at it. WA is 78 if you add up all these and WB is 153 if you add up all these things. So, once you do that, now we go to the table, this one corresponds to the lower one and that one corresponds to the higher one. So, we look at 10 and 11. So, we get 95% is 86 and 99% is 77. So, if the data which you get 78 is smaller, okay. So, NC is 10, that is the smallest comes here and the largest comes here. So, this is 11, this is 10, okay. We will reject if the rank sum of the control group is less than this 86 at 95% or less than 77. So, what do we get? The answer is 78. So, here 78 is less than 86, okay. So, at 95% or alpha of or probability of 0.05 we can reject the null hypothesis. So, what is the null hypothesis? The null hypothesis is the blood glucose level is the same for the control as well as those suffering from Huntington disease, and as per this we got a number of 78, that is the smallest number, and when you look at the smallest number and compare it here, this number is larger. So, we reject the null hypothesis. Okay. So, we accept this alternate, that is control will have lower H. Do you understand? So, you look at this table and then this rows correspond to the lower data points, this corresponds to the higher data points. In this case this is control and in this case this is the Huntington disease. Okay. So, if you take the 95% you get 86, but when you add up all the control ranks we get it as 78, because 78 is lower than 86 we reject the null hypothesis. If that WA has been larger than 86 then we cannot reject the null hypothesis, but in this case we need to reject the null hypothesis. Okay. So, that is one problem. Okay. So, using the Wilcoxon rank sum test we have evidence to suggest that the 5-hour glucose level for individual with Huntington disease is greater than that for the healthy controls at 95% or p is equal to less than 0.5. Okay. We took this because the 78 is less than 86 at the value of this. Okay, let us look at the paired sample. So, we looked at 2 sample equivalent to 2 sample t test, we got this. Now, dependent samples, that means pair t-test, where you are using the same subjects for control as well as drug. There are two different types of test, one is called the signed test, other is called the Wilcoxon signed rank test. Okay, let us look at the signed test. So, this is used when we have no evidence that the paired differences are not normally distributed. So, if it is normally distributed, it is not difficult, we can use the paired sample t-test, and I taught you how to do that long time back, right. The response is ordinal, that means it is just numerics, there is no independent variable like as a function of time and so on. Used when the response is difficult to quantify. Sometimes we may have situations like better, got worse, no change, marginal change, okay, that sort of thing. But the main drawback of this test is the magnitude of the pair difference is lost, because it is looking at only the signs plus minus, comparing the pluses with the minus, the magnitude how much it is changed is lost, but the other test can help you out on that, the Wilcoxon signed rank test can help you out of that, but the signed test loses it. Okay. So, it looks at the pluses, it looks at the minuses, and then it considers only the non-zero paired differences, okay, if there are 0 you neglect it. So, if you have more of pluses than minus, we can indicate that some type of change has occurred. So, if the null hypothesis is no change is true, we expect pluses and minus to be equal. So, pluses minus 0.5, okay, it should follow a binomial distribution, but if it does not follow with the probability of 0.05, then we can use the test to find out whether it is significant or not. Okay. So, it is quite simple. Okay, let us look at an example which uses the sign test. This was taken from this particular book, reference Journal of Clinical Oncology. So, they are looking at hepatic arterial infusion of floxuridine and cisplatin. These are anti-cancer drug for the treatment of colorectal cancer. Okay. So, 29 patients data was recorded before and after infusion. So, is there any evidence? So, there was an infusion of floxuridine and cisplatin anti-cancer drugs for the treatment of colorectal cancer. It was given to 29 patients, data was recorded before and after infusion. So, is there evidence that patients had a better performance score after infusion? That is a question here asked. Let us look at the data. So, before infusion, so we have there are 29 data points. Okay, before infusion you got this data. Okay, this is sort of a qualitative 0, 1, 2, 3. After infusion, same patients, that is why it is almost like a paired t-test which we used to do for parametric. So, you get like this. Okay. Now, you subtract A minus B, so you get negatives, some of them are zeros. So, you get negatives, some of them are zeros, you get some positives as well, and so on actually after infusion. Okay, what do you do? H naught, no change in performance, of course status quo following infusion, or more specifically median change in performance score is 0. Okay. HA is performance scores improved following infusion, or more specifically median change in performance score is greater than 0, because we are subtracting A minus B. So, we expect it to be better. Okay. If it had been B minus A, that is different, but here we are doing it after infusion and before infusion. So, subtracting A minus B, so we expect it to be better, that means it should be greater than 0. Okay, let us look at this data. So, there are some zeros, so forget about that. So, some negatives are there, that means after infusion is not good, but there are some positives. So, a lot of positives appear to be there. So, we feel that after infusion things are better, okay, as you can see. Okay, now let us add up the negatives, let us add up the positives, forget about the zeros here. Do you understand? Intuitively we may think that infusion has helped, because we have a lot of positives coming when compared to the negatives, but we need to do the proper statistical test. Okay, let us look at these data again. So, we will look at only the pluses and minuses. So, as you can see, the minus 1, 2, 3, 4, 5, 6, plus is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So, you have 11 pluses and 6 minuses in 17 data points. Okay. So, if H naught is true, then we should have a probability of 0.5 for the 17 data, okay. Whereas if not, then obviously we need to use the binomial. Out of 17, okay, out of 17 we get 11 positives, out of 17 we get 11 positives, probability is 0.5, okay. So what will be the p-value? So we failed, and this is the p-value, but the p-value is much larger, so we failed to reject the H naught. So there is insufficient evidence to conclude, although it looks lot of positives, but then 11 out of 17, when you put a p of 0.05, it gives you a probability of 0.166, okay. It gives you a probability of 0.166. Obviously we cannot reject the null hypothesis. There is insufficient evidence to conclude the performance score. We use a binomial approach to calculate the probability, and let me tell you how to get this particular value. So the probability of x greater than or equal to 11 when n is 17 with the probability of 0.5, that is what we need to calculate. So we need to calculate binomial distribution when 11 successes out of 17 with the probability of 0.5, 12 successes out of 17 with the probability of 0.5, 13 successes out of 17 with the probability of 0.5, 14 successes out of 17 with the probability of 0.5, 15 successes out of 17 with the probability of 0.5, 16 out of 17 with the probability of 0.5, and 17 out of 17 with the probability of 0.5, and add all of them, and that should give you this. Okay, let us look at it. We use the same binomial distribution, okay, we use the binomial distribution relationship. So binom 11 out of 17 with the probability of 0.5 false, okay, that should give you so this will become 12 out of 17, then this will become 13 out of 17, this will become 14 out of 17, this will become 15 out of 17, this will become 16 out of 17, and finally this will become 17 out of 17. Okay. So if you add up all these terms together, you will get 0.166, okay, and that is how you get this probability. That this probability tells you probability of more than or equal to 11 in a size of 17 if the probability of occurrence is 0.5. But then the sign test has this biggest drawback, because it does not consider the magnitude of the sign, it just looks at the signs plus, minus, and so on. So in order to overcome that particular problem, we have something called a Wilcoxon signed rank test, okay. It does little bit consider the magnitude. Like I said, sign test, the magnitude or the size of the paired difference is lost, okay. So Wilcoxon signed rank test looks at the sign change, as well as it also considers the magnitude by some sort of a ranking, okay. Generally we use it when they are not normal. Obviously, like I said, we are looking at non-normal distribution and the response is ordinal, like the previous case, okay. So let us look at one problem. This is based on a particular reference here. So resting energy expenditure for patients with cystic fibrosis, this is the example taken from this particular reference. So a researcher believes that patients with cystic fibrosis expend greater energy during resting than those without CF, okay. So these people, so to obtain a fair comparison, 13 patients with cystic fibrosis, 13 patients without cystic fibrosis are compared, okay. So the hypothesis is CF expends greater energy during resting than those without CF. So the data was then averaged out or adjusted for age, sex, height and weight. So the data is given here, okay, cystic fibrosis, okay, these are the data and these are the healthy, okay. So the comparison is cystic fibrosis expends more energy, okay. So what we have done is C minus H, C minus H, C minus H, H. Again then look at the sign difference, this is plus, plus, minus, plus, plus, minus, plus, 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 plus and so on actually. Now you take the absolute difference of this data and then you rank them just like originally we did rank test. So the lowest gets 1, the next one gets 2 and so on, okay, until the highest gets 13. What is signed rank? You put the sign also now, okay. So 2 will become minus 2, 1 will become plus 1 and so on. So this will become minus 5 and the rest all will become plus corresponding rank, okay. So it considers not only some sort of the absolute values as well as it considers the rank, okay. Okay, now you so we have these 13 sets of data, we look at them, then we calculate the positive ranks, sum of the positive ranks and then we calculate the sum of the negative ranks. So negative ranks is 2 plus 5 is 7, positive ranks the rest of them, okay, T plus and T minus, okay. Reject the H naught, it states that there is no difference between the populations if either one of these ranks sum is large and the other is small. So the Wilcoxon signed rank test, it uses the smaller rank from these two ranks, okay, minimum of that row, just like the original rank test, okay, it uses that as a test statistics, okay. So the H naught here is the resting energy expenditure of individuals with CF is equal to the healthy individuals who are the same gender, age, height. That means there is no difference in the energy spent by the CF and non-CF. And HA, the alternate hypothesis is the resting energy expenditure of individuals with the CF is greater than the healthy individuals who have after adjusting for gender, age, height and weight, okay. Okay, so we are doing this paired difference, 0 for H naught, greater than 0 for HA, do you understand? Okay, so we take the smaller of the two, okay, in this case the minus which is 7, okay. Now is T7 much smaller for the and then calculate what is the p value using the Wilcoxon signed rank test or statistical, okay. So we look at the Wilcoxon signed rank test table. So we have this degree the number of data points, we have the two tailed and one tailed. Let us look at the one tailed. So 21 and 12 we get observed value is much less than these values. So we reject the, so out of the 13 and 7, okay. So we take the 7 here, okay, 7, okay, and the total number of data points is 13 and here it is 7 is the data we are talking about. So we go to the total number is 13, okay, and we are comparing with 7. So you should get for 95, okay, or 99, 21 and 12. So these numbers are much larger than the 7, okay. So reject H naught at even p is equal to 0.01, okay. Do you understand? It is exactly like the previous signed rank test. We were looking at the table, okay. Here the total number because it is paired we have only one set of number, whereas in the other rank test you remember we had rows and columns because we had it is almost equivalent to a 2 sample t test. Then these test statistics must be lower than the table value to reject null hypothesis. So we got 7 and here we are having 21 or even 12. So these are much larger than the test statistics. So we reject the H naught at a p value of 0.01 actually. Do you understand? So individuals with cystic fibrosis have a larger resting energy expenditure when compared to healthy individuals at a p is less than 0.1. Do you understand? So how to do this problem? So we looked at two types of non-parametric test, one for equivalent to 2 sample t test, okay, the other one is equivalent to a paired sample t test, and corresponding sign test, rank test, then we have the paired rank test and so on. Each one of them have their own tables for comparison. Okay. So, we will continue on this non-parametric test in the next class also. Thank you very much.